Hello everyone, today we're going to be talking about Physics 252, week 7, problem number 4. In this problem we are asked to calculate the frequency at which two speakers in phase will produce their maximum sound intensity. So just looking at the intro to this problem here, our speakers are driven in phase, which is important to note because they're going to be similar. They're increasing in pitch. Taking a look at the position here, we're given two different people, Janet and Brad, and they're standing at different positions away from these speakers. The reason that we can draw our drawing like this is normally we would have or for example, if the problem asks us to find two speakers in a plane and kind of calculate the difference between them. So we had one speaker here, excuse that drawing, but we could geometrically calculate, if Janet was over here, then we could find the path length at which she was away from the speaker. But since it's in one dimension, we can just go straight across here. And so, yeah, looking at the problem here, so maximum sound intensity is given at the point of maximum constructive interference. So at this point of maximum constructive interference, we have our two waves. So let's have one wave here, and then we had, let's say, one wave here, and they're just kind of slowly moving towards each other. And it would be the point at which the crests of the wave match. So let's say it would be right here, something just right in the middle. That's going to be where you're going to get the highest frequency in our case. So the reason that I have our destructive here, you could find the minimum sound intensity, but I just thought it would be cool to include it because you can really take all of the same following steps and just do the same thing for destructive. So looking at what I have here, this is just going to be our path length, and this is going to be our velocity of sound in air. So moving into the problem for Janet here, just taking the difference in path length, calculating it to be 1 meter, and from here we can set this equal to the mode of the wave and the wavelength of the wave. And from here, just kind of doing some simple algebra, I've decided to include the mode for the first and second harmonic for both of these. So that's just as an example, if you will. But here, for just continuing this set of algebra here, we can find our frequency given this equation here, which we used a lot in week 6, where frequency is equal to velocity over lambda. And we end up, if we simplify, we end up getting that frequency equals the mode times velocity for all values of m in this Salin right here. So this signifies all real integers that are positive. So it's m can be anything within this set, and since this set is all real integers, all real positive integers, and this is just based on the fact that for your mode, you can kind of increase a harmonic 1, 2, 3. It doesn't have to be odd or even in this case because it's open. It's an open system. So yeah, just moving on, doing the exact same thing here. And just our only difference here is our path length, our change in path length, so that we just see that in the final equation here as frequency is equal to the mode times velocity divided by 2, where our mode is any real positive integer. So thank you guys for watching. I hope you found this video helpful, and have a great week.